Hi, this is Naresh Kumar Gurulingan. I am pleased to present a work on curbing task interference using representation similarity-guided multitask feature sharing. This is a joint work with Alaya Arani and Baram Zunus. In multitask learning, the parameter shared between all tasks serves as an inductive bias that enables information sharing among tasks. Since tasks share parameters, the inference costs are also reduced. Tasks could either share complementary information or conflicting information. When the shared information is complementary, tasks can improve each other and lead to generalization gains. On the other hand, if the shared information is conflicting, tasks would interfere with each other, leading to drop in generalization. One way by which existing works address task interference is by grouping similar tasks. This grouping could be done at the network level, where if a task is dissimilar, it is learned in a new network altogether. However, grouping tasks at every layer could be a better alternative, as the notion of similarity could vary based on local task representations at different layers. Layer level grouping across all layers could be done directly based on single task networks. However, this does not account for the variability of task similarity depending on how tasks have been grouped in previous layers. Our work revolves around the question, could accounting for this dependence better curb task interference? In progressive decoder fusion, grouping at a decoder layer is done based on a trained network where grouping has been done at all previous layers. We consider 5 different tasks, namely semantic segmentation, edge detection, depth estimation, surface normals, and autoencoder. We assume that the encoder is always shared among all tasks. C represents the number of decoder stages where a stage is a set of layers. We consider these C locations for fusion. After the decoder, each task always has its own head. Fusion is done stage by stage in a progressive fashion as is illustrated in the figure. Towards the left is the initial train network. After fusion at stage 1, we get the second network where all tasks are fused in the first stage. Here, we look at the algorithm of progressive decoder fusion. The grouping decisions at a stage is done using CKA similarity between all pairs of tasks that could be grouped at the stage. The initial network with separate decoder for each task is first trained to convergence. Using this network and a subset of training data, we calculate the CKA between the output task representations of stage 1. The grouping algorithm then determines a grouping such that the task similarity within each group is maximized. Tasks at stage 1 are grouped using this grouping and the resultant network is trained until convergence. Next, using this new trained network, tasks grouped together in stage 1 are further grouped in stage 2. This new network is retrained and the process is repeated for all the remaining stages. To test the effectiveness of PDF, we first present the baselines. The 1DE network has a single shared decoder for all tasks, while the SEPDE network has a separate decoder for each task. We evaluate the two networks in distribution validation data, out of distribution data by adding different types of corruptions to validation data, and robustness to PGD adversarial attack. The SEPDE network has better generalization and better robustness to PGD attack when compared with 1TE. 1TE likely suffers from task interference, leading to drop in generalization and robustness. Here, we show that the task similarities change depending on previous layer groupings. We first compute the CKA similarity matrix across all tasks in stage 1 using SEPDE. Based on this matrix, S and E form one group and D and N form another group. In the top row, we present the similarity of these task groups determined offline at all stages by using SEPDE. This method does not consider the effect of grouping these tasks in previous decoder stages, as these tasks remain ungrouped in SEPT-E. We see that the similarity reduces in later stages, likely because the task representations diverge. In the bottom row, we present similarity between tasks using PDF, where the similarities under each stage is obtained from the fully trained network with grouping done up to the previous layer. We note that the tasks become increasingly similar. This is likely because each stage now gets an input representation shared among tasks in the group. Next, we look at the generalization and robustness of offline and PDF grouping, presented as relative improvement of segmentation and depth over 1DE. In majority of the cases, PDF grouping provides improvements over offline grouping while being more inference efficient. Next, we look at the consistency between the prediction of two sets of tasks. Higher consistency between different task predictions could mean that the task interference is lowered. Semantic consistency refers to the consistency between segmentation and edge predictions. Geometric consistency refers to the consistency between depth and surface normals predictions. In 2 out of 3 cases, we see that the prediction from PDF network is more consistent than the prediction from offline network. SEPT-E network shows high consistency, which could mean that there is more room to reduce task interference. Conclusion: we proposed progressive decoder fusion to progressively combine task decoder layers. PDF accounts for change in similarity at a layer based on sharing in all previous layers. We showed that PDF can improve generalization, robustness, and inter-task consistency. As future work, the training time of PDF can be improved, and the encoder can also be considered for fusion. Thank you. For any questions, please use the provided contact details.